Hello, students, and welcome to NMR lecture number 4. This one is all about this phenomenon known as spin-spin splitting. So, we talked about in the last video the phenomenon of chemical shifts. Chemical shifts, you'll recall, is when a signal gets shifted downfield because of some functional groups that are nearby, right? Up here we have 0, where TMS is, and most of the time our signals are actually down here to the left because these functional groups will suck electron density away from the hydrogens and create a larger Larmor frequency. So that's tool number 1. You're going to be using your chemical shifts a lot. Don't forget to use your free gift, your sample proton chemical shift handout to figure things out. But you have more than just that one tool, right? So we're building for you a toolkit to be able to read and interpret and analyze these NMR spectra. So that is tool number 1, chemical shift. This video is about tool number 2, which is known as spin-spin splitting. Spin-spin splitting. And the two spins that we're talking about here when we talk about spin-spin splitting are two hydrogens that are near each other, right, which we will call neighbors. So let's have a look at this. Okay, so some signals get split into more than one peak. In this case, if we were reading this spectra, we would say that there are two different signals. A signal arises from one hydrogen or a group of hydrogens that are the same as each other. In this case, we have this hydrogen attached here and this hydrogen attached here. So with two hydrogens, we're expecting two signals, and that's what we see. This is a signal, and this is a signal as well. We notice, however, that in this particular case, the signals are not single peaks. Each one is split into two peaks, real close to each other. We call two peaks really close to each other a doublet. So this is a doublet, that's one signal, and this is also a doublet, that's the second signal. Now, we have two signals here. Only one of those signals arises from this red hydrogen. So let's see if we can figure out which one is which. And there's a clue based on the structure of the molecule and based on the chemical shifts. So use your table and find chloride and then find iodide on your table of chemical shift and make a guess as to which one of these signals is the red hydrogen. So pause the video, see if you can't figure out, is the red hydrogen correspond to this signal or that signal? Go. Okay, hopefully you took a stab at this. When you look it up on your table of chemical shifts, what you see is that chlorides have a characteristic shift between 3 and 4. That's for one chloride. And iodides have a chemical shift between 2 and 4. Now there is some overlap, right, between 3 and 4 and 2 and 4, but on average, hydrogens that are near chlorides have a bigger chemical shift, right? And because there's two chlorides, we know it's going to be even further downfield. So two chlorides probably is going to be a bigger effect than two iodides. So if we had to guess, we would say that this is probably, right, the signal that corresponds to this hydrogen, just on the basis of the chemical shift and the fact that chlorine is more electronegative than iodine. And we have a blue hydrogen, of course. That blue hydrogen is giving rise to this signal right here. So far, so good. But what the heck is a splitting thing, right? Why is each signal actually split in two? That seems nutty. Well, imagine this. Let's consider again the red hydrogen. The red hydrogen is making both this peak and that peak, right? Its chemical shift is determined by B local, the local magnetic fields. And most of B local, a huge part of B local, is caused by those circulating electrons, as we talked about. Those electrons spin around and create a magnetic field opposed to the applied field. But there is actually another part of B local that is caused by neighboring hydrogens. Remember, these hydrogens are acting like mini little magnets. So if you're red and you're looking around and you're thinking about what magnetic fields are out there, what you're feeling the B applied from the electromagnet. You're feeling B local from electrons spinning around. And you're also feeling the effect of your buddy next door who's a little magnet. And remember, because your buddy next door is spin 1/2, he will either be spin up or spin down, right? If there was only one single molecule in your whole test tube, you would not see spin-spin splitting, right? You would just see one single peak here. But remember, in a sample, in any drop of this compound, there's billions and trillions and quadrillions of molecules, right? In roughly half of those molecules, if you're the red hydrogen and you're looking over at your buddy is going to be spin up, right, in the same direction as the magnetic field. In those half of all cases, your buddy being spin up is going to add to the total magnetic field that you're feeling. What that's going to do is it's going to slightly increase B net from what it used to be. And remember, a bigger B net is going to give you a bigger Larmor frequency, which is going to show up to the left, which is slightly downfield. So the 50% of times where your buddy is spin up, that's going to give rise to this little peak right here. And of course, 50% of the time, your buddy is actually going to be spin down, right? Because roughly half of these are up and half of these are down, approximately. If your buddy is down, now your buddy is opposing the applied field, which is going to slightly decrease B net, decrease the Larmor frequency. So now, in the 50% of molecules where your buddy is down, that's going to give rise to this peak right here. You see how that works? So this is an added contribution to B local that results in two slightly different versions of this molecule, right? And the same thing is true with this guy, right? This guy also has one neighbor. He could be up or down. That's why this is also split in two. Okay, so this is the characteristic pattern that you see when you have one neighbor. One neighboring hydrogen tends to cause a signal to be split into two. Of course, it can be a little more complicated. Let's look at this one. So here's another molecule. This is chloroethane, this puppy right here. First off, how many signals do you see? How many signals do you see? The answer is there are two signals, this over here and this over here, right? And we see that each signal is split up into a multiplet, but there are two signals. That must mean that there are two different types of hydrogens, right? All of the hydrogens, and we'll talk about this a little bit more later, but all of the hydrogens on the same carbon are what we call magnetically equivalent. When hydrogens are magnetically equivalent, they give rise to the same signal. So two signals should correspond to two groups of hydrogens, one group on each carbon in that case, right? So if we look up at our structure up here, we have one group is here on that carbon near the chlorine, and there's another group over here, right, on this carbon further away from the chlorine. So let's ponder this for a minute. Which group do you think is making the red signal, and which group is making the blue signal? Well, we have some clues, right? The clues are the chemical shift. We're going to talk about splitting in a minute, but let's just think about chemical shift, for example. One chemical shift is around 1.5, 1.4. The other one is between 3 and 4. So take a minute, ponder, pause the video, and predict which group of hydrogens makes which signal. Go. Okay, hopefully you got a chance to do a little predicting. What you hopefully figured out is that these hydrogens are on a carbon next to a chlorine. And if we look at our table of chemical shift and we look up chlorides, it says they're between 3 and 4, right? And there's only one signal that's between 3 and 4, and that is this one. So these reds are those two hydrogens over there. And of course, conversely, not the carbon, of course, but these three blue hydrogens correspond to this blue signal here. One of the things you might notice is that on your sheet, it says primary hydrogens have a chemical shift of about 0.9. And this one's actually a little bigger than 0.9. That, of course, is because there is some functional group further on away, and that has some slight effect here. So don't let that throw you, right? Primary ones are only 0.9 if there's absolutely no other functional groups anywhere nearby. If there are functional groups somewhere more distant, you won't see that characteristic chemical shift listed on your table, but it will be shifted a tiny bit down past 1. Okay, so here we go. These are the red hydrogens. These are the blue hydrogens. Why are they split in these wild multiplets? All right, same idea as what we just talked about, except now it's a little more complicated, right? So let's consider the red hydrogens for a minute. Why is their signal split into 4 peaks? And at least as importantly, or more importantly, notice they're not 4 equal peaks, right? These two are small, and the two in the middle are big, right? We call this signal a quartet. So it's a quartet, but it's a special quartet where the two in the middle are big and the two on the outside are small. But let's imagine what's going on, right? So it must have something to do with these blue neighbors, right? When red looks over and looks at the blue neighbors, there's some different possibilities. Each of these 3 hydrogens is like a little magnet. Each one can be spin up or spin down. How many different possibilities are there? If you have 3 different ones and they're all independent, they're all unique, and each one could be up or down, how many different possible combinations of up and down are there, right? When red looks over and looks at those 3 blue ones. If you're feeling ambitious, take a minute and sketch out what are the different possible combinations. One possible combination is they could all be up. Another possibility is they could all be down, right? What are the other possibilities? Take a minute and sketch those out. Okay, hopefully you did a little thinking about that. How many different possible combinations are there? There's 8 total, right? They could all be up. There's one way that that could happen. They could all be down. There's one way that that could happen. You could have 2 up and 1 down, but there's 3 different ways that you could have 2 up and 1 down, right? That one could be down, or that one could be down, or that one could be down, right? And in the same manner, there's 3 different ways that you can have 2 down and 1 up. So there's 8 different possible combinations, but 3 of those are the same as each other, and 3 of them are the same as each other, right? So the 2 downs and an up and 2 ups and a down, those really are kind of the same thing. So that gives rise to this structure right here, right? So this little peak on the edge here, this one is when all 3 of the neighbors are up. The one on the other side is when they're all down. And the 2 larger peaks in the middle are when 2 of them are up and 1 of them is down, or vice versa, right? So because there's 3 different ways that you can get this combination of 2 downs and an up, or 2 ups and a down. That's why those middle peaks are bigger. So what you'll get is a quartet. All of these quartets will always have the same ratio. They'll always have a 1 to 3 to 3 to 1 ratio, right? 8 different total possible combinations. And there's a probability of 1 to 3 to 3 to 1 based on what you're going to get, right? Okay. The blue hydrogens, in contrast, when they look over, what they're seeing is a triplet, right? So what are the different possible combinations? When blue looks over and sees only 2 buddies, right? Blue only gets split into 3. That's because they could either both be down or both be up, or one could be up and the other could be down, or they could switch, right? So there's 2 different 1 up and 1 down possibilities. And that's why you get a 1 to 2 to 1 ratio on a triplet. Notice that these ratios, right, follow Pascal's triangle. Ooh, ah, right? So if you have a singlet, it's just 1. A doublet is a 1 to 1 ratio. A triplet is a 1 to 2 to 1 ratio. A quadruplet, a quartet, not a quadruplet. A quartet is a 1 to 3 to 3 to 1 ratio, and so on and so forth, right? These follow Pascal's triangle because you're looking at combinatorics, right? This is that classic, N choose K problem in math. So that's the exact same thing here. We're counting up the total number of probabilities and figuring out how many fall into each category. Okay, back to chemistry. This gives rise to what we call the N+1 rule. The N+1 rule. This will simplify all of this so you don't have to do a bunch of math and a bunch of N choose K anytime you have to deal with problems like this. So the basic rule for spin-spin splitting is known as the N+1 rule, which is the number of peaks is equal to the number of neighbors plus 1. The number of peaks is the number of neighbors plus 1. So the capital N doesn't just stand for number, it stands for neighbors, right? So for these red hydrogens have how many neighbors? They have 3 neighbors. So 3 plus 1 is 4. So red gets split into 4. And if you're thinking about the blue hydrogens give rise to this signal. Blue has how many neighbors? Blue has 2 neighbors. 2 plus 1 is 3, which means blue gets split into a triplet. So what exactly is a neighbor? A neighbor is not on the same carbon. A neighbor is any hydrogen that is 1 carbon away. In other words, it's on a carbon that is adjacent to the carbon that that hydrogen is on. So red and blue hydrogens are neighbors because they're not on the same carbon. They're 1 carbon away. Those are the only time you get splittings, or for our purposes, the dominant time where you're going to see splittings. Let's look at this one for a minute. 2-methylpropane right here on the left. All right, the pink has 9 neighbors. Can you believe 9 neighbors? Well, pink is on this carbon right here, right? Which carbons are 1 carbon away? This one, and this one, right? So all 9 of these are neighbors to pinky. So when you look at pink, that pink hydrogen signal is going to be split into 10 peaks. Oh my goodness. All right, so here's a question for you. Let's suppose we're looking at these hydrogens right here. My question is, for these hydrogens right here, how many neighbors do they have, and what will their signal look like? Take a minute and predict. Pause the video, then we'll discuss. Okay, these hydrogens down here, how many neighbors do they have? Well, they're on this carbon, so they're not neighbors with each other. We got to go 1 carbon away. 1 carbon from this carbon is this carbon. How many hydrogens does this carbon have? This carbon only has 1 hydrogen, pinky, right? So these down here only have 1 neighbor. Because they have 1 neighbor, their signal is going to be split into 2 to make a doublet. And in fact, because of symmetry, these and these and these are actually all the same. So all 9 of these hydrogens are going to give rise to the same signal, and it's going to look like a doublet because they all have 1 neighbor, that one. Let's talk about magnetic equivalence a little bit more. Let's consider ethane for a moment. If you put ethane in an NMR instrument and look at its spectra, what might you see? Will there be splitting? The answer, perhaps counterintuitively, is no. This is an actual NMR spectrum for ethane, and there's no splitting at all, right? It's not like, originally we just said if you're on a carbon next door, then you're going to be neighbors. Here's a case where that's not true, right? And it's not true because of magnetic equivalence. Because of symmetry here, these hydrogens look exactly the same as those hydrogens, so they're not going to split each other. Because they're in the exact same chemical environment, they're experiencing the exact same B net, they are magnetically equivalent, and so they only give rise to 1 signal, and they won't split each other. Okay. That's the end of this video. There's one more video on tools, and that's about integration. That's coming next. Talk to you soon.